Hello, welcome to the DataFest 2020 Uncertainty in Machine Learning track. My name is Andrey Malinin, and in this video I'll tell you about how to estimate data and knowledge uncertainty. So in the previous video we discussed why uncertainty estimation was important, and we detailed the two sources of uncertainty: data uncertainty, which is a known unknown and derives from class overlap and homoscedastic and heteroscedastic additive noise, and knowledge uncertainty, which is an unknown unknown and has to do with situations where inputs come from regions which are either not covered by training data or sparsely covered by training data. In other words, dataset shift. Now, data and knowledge uncertainty are idealized sources, and real data has elements of both. Total uncertainty is derived from data and knowledge uncertainty. Now, finally, this is important because the appropriate action we'd like to take based on our estimates of uncertainty depends on the source. If we're doing error detection, we'd like to do total uncertainty. If we're doing anomaly detection or active learning, knowledge uncertainty. So in this video, we'll talk about how to estimate both of these sources of uncertainty. Let's focus on data uncertainty first. So, as we talked about before, for classification, data uncertainty is because you have class overlap, and for regression is when we have additive noise to our function. Now, data uncertainty is a property of the underlying data distribution, py of x for classification, or py bold of x for regression. And as we are trying to model this underlying data distribution, we need probabilistic classification and regression models. Now, thankfully, almost every single classification model you've ever used is probabilistic. If you're using a neural network, you have a softmax, it's probabilistic, you're good to go. However, most regression models tend to be not probabilistic. They tend to just predict a particular score, and they're trained with an L2 loss. In this work, or in this particular application, we need to use probabilistic regression models. And typically you have some kind of model which parameterizes a distribution over the output variable. For example, you can predict the parameters of a normal distribution. So your model predicts the mean and the variance, and you define a normal output distribution over your target y. And generally you can consider many different types of distributions, like a Cauchy distribution, a Laplace distribution, a t distribution. Doesn't matter which one, we'll stick to the normal one here because it's simple and it works pretty well in practice. However, be mindful that choices of output distribution are important in this case. So we'll do a little reminder based on classification. So we'll just talk about classification for now because the story for regression is generally the same. So we care about a property or a measure called entropy of the distribution. Now, entropy is the expected negative log probability of a class. Now, when a distribution has low entropy, it Now, we'll focus in this discussion mainly on classification because the story for regression is generally the same. Now, an important property or an important measure which you must understand is entropy of a distribution. Now, the entropy is defined as the expected negative log probability of a class across all classes. If a distribution has low entropy, it's sharp around one of the classes. And when the distribution has high entropy, it tends to be more flat or more spread out. This is also true for regression problems, but we'll talk about that at a later point. Now, the true level of data uncertainty is defined as the entropy of the true underlying distribution of data. Now, we don't actually have access to this distribution, but our model is probabilistic and has been trained on this data. So if we measure the entropy of our model, it'll give us an estimate of the level of data uncertainty at this point. And this happens if you train your model using maximum likelihood estimation. Now we'll have a little bit of math. I'll walk you through this, so don't be scared. So maximum likelihood estimation is the same thing as cross entropy loss. It is the same thing as log loss for binary classification. It is the same thing as minimizing the KL divergence between your model and the true distribution. And let me show you why this is. So let's imagine here on the first line, we're taking the expectation with respect to samples from the true distribution. This is our data. And we'll be minimizing the negative log probability of a particular class to which the current input y belongs. Now, if we break out the conditional distribution for y given x into here and take expectation of the indicator, it just sort of multiplies in like this. And this is your standard cross-entropy loss, which I'm sure you're very all familiar with. We're taking expectation of our inputs x, minimizing the cross-entropy between our model and a true underlying distribution. Now, using some very simple mathematical manipulation by adding the entropy of the true distribution and then removing it, we can rearrange this to show that the max likelihood loss is equivalent to having to minimizing the KL divergence between your model and the true distribution, plus you have an irreducible term, which is the entropy of the true underlying distribution. So the lower bound achievable on your cross-entropy loss is the entropy, assuming you're training on lots of data. And you can, in principle, minimize this KL divergence. So, data uncertainty is captured if you train your model using max likelihood and you minimize the loss, then data uncertainty should be fully captured. However, there are some very important conditions here. Firstly, you must have sufficient training data. The statement I have made is true when you have infinite training data. But in practice, that is never true. You always have a finite data set. This also means that if you're overfitting to your training data, you will have bad estimates of data uncertainty. Secondly, your model must be powerful enough to capture the true distribution. For classification, this generally means that you need to have a big enough neural network. For regression, however, it also means that you must have chosen the correct output distribution. Your data may not be distributed normally. We'll talk about this a bit later. And finally, it is important that your model is not underfit and not overfit. So these are conditions under which max likelihood training will yield a model which captures a good estimate of data uncertainty. Now, again, the challenge. This is in general challenging. Models can be underfit or overfit, and this is a fundamental issue in machine learning. It is also challenging to correctly generalize. Your data set is finite. Your model can yield bad predictions and bad estimates of uncertainty far from the training data. And in fact, this is when you have high knowledge uncertainty, which we'll talk about next. Similarly, your model can also yield bad uncertainties and predictions in regions with limited training data. And finally, it is challenging to choose the correct output distribution for regression tasks. We can choose a Gaussian distribution or the normal distribution, and it's standard, and it presents the least number of assumptions about the world, which is why it's a good standard distribution to use. But the world isn't always Gaussian, and your true underlying distribution of targets y can be multimodal and non-symmetric and many other things. And if you didn't choose the correct distribution, you will not capture the correct level of data uncertainty. And in fact, this choice is non-trivial. It's hard to know a priori what is the correct distribution. So those are the limitations, but the point is that if you have a probabilistic model and you do maximum likelihood, you're more or less good to go. So we've discussed data uncertainty. Now let's talk about how to estimate knowledge uncertainty. Now, for knowledge uncertainty, we need to have ensembles of models. Here I'll describe a Bayesian framework for ensembles, but it doesn't really matter. We don't have to use a Bayesian framework, it's just a nice one. Now let's imagine you have a posterior over model parameters. You have defined a prior over model parameters here. You have a likelihood, you have your evidence, and you've obtained via Bayes rule a posterior over model parameters. This gives you the distribution over likely models which have generated the data you've seen. So basically, models sampled from this distribution should agree on data they have seen, and they can disagree on data they haven't seen. And this is an important property. Now let's imagine we've taken this distribution and we've sampled multiple different instances of model parameters from it. And now we have obtained an ensemble of probabilistic models. Now in typical Bayesian inference, for prediction, not uncertainty estimation, but for prediction, we typically average together the probabilities of models in this ensemble. This is something called the predictive posterior. So we've taken these models, we've parameterized multiple probabilistic classification models, and for the same input, for a particular input x star, we have averaged together their probabilities. This gives us our predictive posterior, which we then use to actually predict the class and so on and so forth. Now let's imagine what happens to this ensemble of models when we show it several different kinds of inputs. Now first, let's imagine we have shown it an input which all the models understand. It's a low data uncertainty input, which all the models understand. Here, the models should all yield the same prediction. All models agree on the data, and they agree that it's low data uncertainty, and they confidently predict that it's the class 1. When we average together all the probabilities across the ensemble, we have a predictive posterior which looks just like the posterior of every individual model. Now, if we give an input which all the models understand, but it has high knowledge uncertainty, for example, it lies on the decision boundary between 3 classes, we expect that all the models in the ensemble will yield a high entropy distribution over classes. The ensemble will be consistent. All the models predict the same thing. And again, the predictive posterior is the same as for each model. Now note, here the predictive posterior is high entropy because we are uncertain, because we have high data uncertainty. Now finally, imagine I've shown the ensemble something which none of the models understand. I mean, for example, let's say I've taken an audience of people, replaced them with neural networks, have shown them all this Rorschach test, and asked them what they all see. And then every single person or every single neural network, doesn't really matter, says something very different. This is exactly what's going on here. We'd like the models to all yield very different predictions when they see something they don't understand, because this input comes from a region which is very far from the training data, and therefore models sampled from this posterior will describe it differently. So each model yields a different prediction. The ensemble is now very diverse, but the predictive posterior is also high entropy because we've averaged together very many different diverse probability distributions. In the end, we achieve a high entropy uniform probability distribution. So when the ensemble is low entropy and consistent, we're confident. When the ensemble is consistent and high entropy, we have data uncertainty. And when the ensemble is diverse and the predictive posterior is high entropy, we have knowledge uncertainty. Now we can visualize this in a different way. So what I have here is something called the simplex. The simplex, in this case, a 2-dimensional simplex, is a triangle. It represents the space in which every single point represents a probability distribution over 3 classes. If we have higher dimensional simplexes, we can describe distributions over more classes. Now, we can visualize the behavior of the ensemble in these 3 cases. When the ensemble is confident and we have low data uncertainty, we have a tight cluster of points at the center, at one of the corners. So let's say this is class 1. All the models agree that it's class 1, and they generally give high confidence, low entropy predictions in the region of class 1. Now, when the input is high data uncertainty, let's say it's on a decision boundary, all the models agree that it's high data uncertainty. All the models agree that we can't distinguish between classes. All the models give us high entropy distributions over classes, which will live at the center of the simplex. Finally, when we show the ensemble something that none of the models understand, we expect the ensemble to give us very diverse predictions, and the predictions of the ensemble will sort of be all over the simplex, will be everywhere. This is one way of visualizing what we want from the ensemble. Now, having talked about pictures, let's switch to math, because in the end, we need to actually get some numbers for this uncertainty. Now, we have seen that the average prediction of the ensemble is high entropy whenever we are uncertain. When we have high data uncertainty, we have high entropy predictive posterior. When we have high knowledge uncertainty, we also have a high entropy predictive posterior. So the entropy of the predictive posterior of the ensemble, or the entropy of the average prediction across the ensemble, is a measure of total uncertainty. It's uncertain whenever we are, it is high entropy whenever we are uncertain in general. Now, if we consider the entropy of each individual model in the ensemble, so we model the expected entropy, or we just basically model the entropy of each model and then average the entropy across all models in the ensemble, we will have an average estimate of data uncertainty, or the expected data uncertainty. Now, this is in general not the same as the entropy of the predictive posterior, although they can still coincide if the ensemble is consistent. So we've obtained estimates of total uncertainty, we've obtained estimates of data uncertainty. So how do we get knowledge uncertainty? It's actually quite simple. We can consider the difference between the entropy of the predictive posterior and the average entropy across the ensemble. And this measure is something called mutual information. And it's called that for a lot of pretty cool information theoretic reasons. It's also called Jensen-Shannon divergence and so on and so forth. But that really doesn't matter. What matters is that it is a measure of ensemble diversity. If all the models in the ensemble give us the same prediction, then the average prediction is the same as each individual prediction. Therefore, the entropy of the average prediction will be the same as the average entropy of each individual prediction, and the difference between these two will be zero. However, when the models are diverse, the entropy of the average prediction will be higher than the average entropy of each individual prediction. And this, for example, follows from Jensen's inequality and so on and so forth. And you can show that this is always true. This difference will be greater than zero if the models are diverse. And depending on how diverse the models are, this difference becomes bigger. So the more diverse the models, the bigger the mutual information, the bigger this difference. So this difference is now a measure of knowledge uncertainty. Now, why I call it mutual information is because theoretically speaking, this measure defines the mutual information between the prediction and the model parameters. If the ensemble is very diverse, then we can uniquely identify which model made which prediction because the predictions are so diverse. When the ensemble is consistent, we can't figure out which model made which prediction because all the predictions are the same. But that really doesn't matter. What I really want you all to take away from this is that this is a measure of how diverse the ensemble is, and therefore knowledge uncertainty. That's about it. Now, let's just talk about regression very quickly, because the story is the same, but unfortunately for regression, you can't actually calculate the entropy of the predictive posterior, because when you average together a bunch of Gaussian distributions, it forms this complex multimodal distribution which you can't tractably compute the entropy for. So, let's imagine you have an ensemble of probabilistic regression models. So you have an ensemble of these probabilistic regression models. Each model gives you an estimate of mean and standard deviation. You can use for the ensemble something called the law of total variation to obtain estimates of knowledge and data uncertainty. So the overall variation, the total uncertainty, equals the variance of mu plus the average variance of each model. So it's 1 over m, sum of the variance of the mean, where mu bar is just simply the average mean across the ensemble, plus the average variance of each model. Now this is the total uncertainty, and the average variance is the data uncertainty, and the variance of the mean is knowledge uncertainty. Now, this is generally is very similar to mutual information in spirit. However, it is important to note that this is not scale invariant. And in regions where your model makes very large predictions, let's say you're measuring depth, and in certain regions of your image you have very low depth, and in some regions of your image you have very high depth. Your uncertainties at different depths cannot be really compared very well, because their scale is naturally different, and therefore the variance of the mean and the average variance will be very different between low depth portions of your image and high depth portions of your image. This is one of the problems of using non-information theoretic measures of diversity. Nevertheless, it's a useful thing to use, and it's very simple. So we'll just stick to this. Now, there are many ways. So I've just kind of now I've avoided the topic of how we actually construct the ensemble, and there are many different ways of how you could actually do this. Now, there are some are more complicated, some are less complicated. You can use Monte Carlo dropout, or stochastic gradient Langevin dynamics, or fast ensembling via mode connectivity, or stochastic weight averaging. Doesn't matter. In fact, you can even use bootstrap or deep ensembles, where deep ensembles are models trained on the same data but from different random initializations. And then in one of the next lectures, Arsenia Shucha will tell you about how to compare these methods and which ones are better. But at this point, I will not really dwell on this. Just know that there are many different ways in how ensembles can be made. Some are better, some are worse, some are more expensive, some are cheaper. But the point is, I really want to talk about the limitations of ensemble methods. And there are generally two fundamental ones. Firstly, this is very expensive in terms of computation and memory. Generating an ensemble can be challenging because you need to store multiple models and you need to train multiple models in some way. And sometimes there's ways of making an ensemble in a cheaper way, but nevertheless, regardless of how you make the ensemble, inference or prediction is always m times more expensive because you have to run inference over m different models in your ensemble. This is a significant limitation to the approaches we discuss here. And in one of the later videos, Bruno Mlodzinich will tell you about how we can make this faster and cheaper and overcome one of these limitations. The second limitation is that in general, it is hard to guarantee that your ensemble is rich and diverse. In general, having diverse parameters or very different model parameters does not mean that you will have very diverse functions or models. And often it is the case that if you do generate an ensemble of greater diversity, it is more expensive to compute this because you have to run these, for example, Monte Carlo sampling approaches for longer, or you have to individually train multiple different models, and that's more expensive than doing things like Monte Carlo dropout, for example. But this tends to give more diverse models. So these are the fundamental limitations. So thank you. This brings us to the end of this video. Hopefully you've liked it and learned something interesting. Stick with us. In the next video, I'll tell you about how to assess the quality of the estimates of uncertainty which we have derived using the methods described in this video. Thanks, and see you later.